So in today's video, we're going to go ahead and see how we can use polynomial long division to help us integrate these complex rational functions. So previously we took a look at how we can use arcsine and arctangent of x to help us with these rational expressions. And now we're going to use polynomial long division, which is particularly useful when the degree of the denominator is less than the degree of the numerator. And so let's go ahead and take a look at a couple of examples. So I'm hoping that everyone here is familiar with polynomial long division. But we will be able to get a chance to review it while we're actually doing this. And these are very good HL math style questions. And so here we're taking the integral of x cubed plus 2x squared plus 2x plus 1 divided by x plus 1 dx. And so here we observe that the degree of the numerator is 3 and the degree of the denominator is just 1. And so in this case, it may be helpful to actually use polynomial long division. So let's go ahead and do that. So here we have x plus 1. And then here we'll have x cubed plus 2x squared plus 2x plus 1. There is also different methods you can use when you have a first degree in the denominator, which would be like the Euclidean algorithm sort of method. But if we want like kind of a more general way to use it, we would just use this long division method because it would apply to higher degrees in the denominator than just one. And so over here, we'll go ahead and just start dividing. We have x cubed divided by x. That just gives us x squared, and we'll put it over the x squared sort of column. And then we can go ahead and subtract and multiply. So x squared times x is just going to be equal to x cubed. And then x squared times plus 1 is just plus x squared. And then when we subtract them, we get x squared, x cubed minus x cubed. These cancel out. 2x squared minus positive x squared. That's just going to be equal to x squared, and then we bring everything down. So plus 2x plus 1. And then next up, we can just do the same process. Here we have x squared. We divide that by x. We end up with plus x. And so we'll put that over the x to the first column, and then we multiply everything out. So we get x times x is x squared. X times plus 1 is just plus x. And then when we subtract, these cancel out. 2x minus plus x is just equal to 2x minus x, which is just x, and then this plus 1 stays the same. And then you'll notice here we're just doing x plus 1 divided by x plus 1. That'll give us 1, and if we want to kind of get the remainder or confirm that it's 0, we do 1 times x, which will give us x, and then 1 times plus 1, which is just plus 1. These cancel out when we subtract, and our remainder is 0. So this was a very nice case where we could actually divide the polynomial and get a remainder of 0. It means that it's a factor of where the denominator is a factor of the numerator. And so now we can go ahead and rewrite this integral in this new form that we got, in this quotient of x squared plus x plus 1 dx. And now it's significantly easier to integrate. We just have a regular polynomial function to integrate. So the integral of x squared is just x cubed over 3. This is just the reverse power rule. And then the integral of plus x is just x squared over 2. The integral of plus 1 is just plus x, and then we have a plus c at the end. And that right over there is our final answer. So we took a very complex looking rational integrand, and we just simplified it into the simple second degree polynomial, and then we just use kind of the sum rule and the reverse power rule. And so now let's look at a case where it actually isn't a perfect factor. The denominator isn't a factor of the numerator. So here we have x to the 5th plus 3x cubed minus 6 divided by x minus 1 dx. And so again, let's go ahead and use the polynomial long division. Again, you could also use Euclidean's algorithm here because you have an x minus 1 in the denominator. It's the highest degree term of the denominator. The degree of the denominator is positive 1. And so then we can just go ahead and put this in. We're going to use this method though just to see, I mean, we'll get the same result either way, but just to kind of get more comfortable with it. So here we have x to the 5th. In this case, what we're going to do, since the degree or the coefficient of the x to the 4th term is 0, we're just going to include a 0x to the 4th because it doesn't really change the value of this expression. And then we get plus 3x cubed. Same thing will be applied to the x squared term. We're just going to add a 0x squared. And same thing for the x term. We're just going to add a 0x and then minus 6. Let me go ahead and extend this. And so now let's just go ahead and start dividing. So x to the 5th divided by x is just going to be equal to x to the 4th. And then we subtract and multiply. So x to the 4th times x is x to the 5th. And then x to the 4th times negative 1 is minus x to the 4th. These will cancel out when we subtract. And then this is a negative times a negative. And we have a 0x to the 4th up here. So this just becomes plus x to the 4. And then we bring everything down. So plus 3x cubed plus 0x squared. plus 0x minus 6. And then we just continue. So x to the fourth divided by x is just going to be x cubed. And then again, we multiply. So x cubed times x is x to the 4. And then x cubed times negative 1 is negative x cubed. And then when we subtract, these will cancel out. Here we'll get a 3x cubed plus x cubed because the negatives cancel. So we get 4x cubed plus 0x squared plus 0x minus 6. Really, the longest part here is actually just the division part. And so 4x cubed divided by x minus 1, that gives us 4x squared. Again, multiply and subtract, we get 4x cubed minus 4x squared. These will cancel out, the negatives will also cancel, this will become positive, and then we get 4x squared plus 0x minus 6, and we're nearly done. 4x squared divided by x is just positive 4x. Again, multiply and subtract, we get 4x squared, right, minus 4x. And then again, these cancel, this becomes positive 4x minus 6. And then finally, 4x divided by x is just plus 4. And so over here, we'll go ahead and end up with a 4x. And then we have 4x times, or we have 4 times negative 1 is just negative 4. And then these cancel, negative 6 minus 4, we end, or negative 6 minus negative 4 is negative 2. And that's our remainder over there, and this is our quotient up here. So now let's go ahead and rewrite this integral. I'm just actually going to go ahead and bring this whole integral down using an arrow so we can have more space to work. So this is just equal to the integral of x to the fourth plus x cubed plus x cubed. We're just copying down the quotient now, plus 4x squared plus 4x plus 4. So let me just fix that plus sign. So plus 4x squared plus 4x plus 4. And then here we have this negative 2. So this is negative 2 over the divisor, which is x minus 1, and then dx. And so these first few terms over here, this is very easy to work with. We know we can just use the reverse power rule. So x to the fourth's integral is x to the fifth over 5. X cubed is just going to be x to the fourth over 4. 4x squared is going to be 4 over 3x cubed. 4x, the integral is just going to be 2x squared. This is all just the reverse power rule and the sum rule. And then the integral of 4 is just plus 4x. And then we have this part over here, the negative 2 over x minus 1. And we can work with this on the side. So this is the integral of negative 2 over x minus 1 dx. We can take this negative 2 out if you would like. And so it will just be equal to 1 over x minus 1 dx. And we know that the integral of 1 over x is just equal to the natural log of the absolute value of x. And so in this case, we have a 1 over x minus 1, and you can do a quick use substitution in your head, or you can write it out if you'd like. But ultimately, you'll end up with negative 2 times the natural log of the absolute value of x minus 1 plus c, of course, because it's an indefinite integral. And really, the way that we did this, we just let u equal to x minus 1, and then du is equal to dx. And then you can just go ahead and make the substitutions, back substitute, and you'll end up with negative 2 times ln of the absolute value of x minus 1. And so then we just go ahead and add this to our final sort of antiderivative over here. We'll get a negative 2, so minus 2 times ln of the absolute value of x minus 1, and then plus c, of course. And so here we get this very crazy looking polynomial that includes this natural log term. And so it's a very intense expression, but it is definitely a much easier integration process when we just use this long division. Again, there are different ways to divide polynomials, but the polynomial long division is the most general form, so that's the one that we covered here. And it's also good to get some revision of it and of the general process. But essentially, this is how you would use polynomial long division, or really just the division of two polynomials in general, to help integrate these complicated looking rational expressions wherein the degree of the numerator is greater than the degree of the denominator. So I hope this helps.